I just quickly reviewed a simple way to calculate two-person zero-sum game. But what happens if you have more actions? And particularly in the zero-sum case, then that kind of thing wouldn't be work, wouldn't be straightforward. But we were able to, we still were able to calculate Nash equilibrium for zero-sum game in the polynomial term. When I say polynomial term, is we respect to the computing term is very quick. We generally regarded to solve the problem. So let's just looking at example. Here we got these two players. They have, in terms of payoff, they opposite to each other, right? And adding together is 0, right? Then we got this player 1, role player, and they play x1, x2. And column player, they play y1, y2. Just looking at this simple case, but we're still looking at two actions case, but they can be extended and naturally in other these more actions case. So the x, y, x, we can indicate the same thing as before, like a mixed strategy, therefore probabilities. So now let's looking at this from role player perspective. Looking at this here, from player 1's perspective. Say suppose role player announce a strategy. Okay, say I'm gonna play 50% chance economy, 50% chance of society. I'm gonna focus on economy with my 50% of my energy. And the rest go really looking on the society, and this presumably, right? It's look suboptimal because you reveal the information to player 2. As we show this Conrad's case, right? If you reveal the information to others, then you probably wouldn't pay advantage unless you have more information, right? Because that in the Conrad case, that player 2, although starting first, but player 2 is a leader because they actually know the player 1 start first because player 1 know the player 2's strategy, so they actually get more information. So in other words, that player 2 revealed their strategy already. So this is presumably a suboptimal, but actually in the zero-sum case, not. So we'll see what happens. So now, give this role player announce a strategy. So suppose I do this, at 50-50, and the column player, and try to minimize the rewards get from role player. In this case, what column player going to do? So he would choose tax cut, right? You can actually verify it. He would choose tax cut because you can actually looking at this probability of these, there, and also a probability of. So if you're choosing this 50-50, right? 50-50, you can do the trick as 50%. You can do the trick as before. They choosing this. Combine this, right? 50-50, and compare whether morality, the tax cut, which one will be better, or they are equal. So in this case, you would choosing tax cut because that give them sort of higher reward. Then, okay, so more generally, you could actually write it down. Let's say the role player's announcement is strategy X1, X2. Then you always write it down. Is say the value of morality is the -3 x1, which is probability going to choosing that, plus the probability you're going to choosing 2 multiplied by 2 is you expected value of if you really strategy focus on morality, right? So the same case you can calculate for tax cut. Then this column player's optimal reaction to the role player's announcements would be say, I'm gonna maximize the, either this one or this one. I'm gonna choosing one which has a higher value, right? And since this is a zero sum, right? Looking at the structure, I can, instead of saying I do this max, and I can do this minimization of the opposite value, right? I can minimize. So instead of maximize those value, I minimize those value, right? Those value. So this is reviewed here. Okay, I minimize those value. So you can write it down everything together. Is this okay? Is that okay? These role player, right? The player one, to figure out x1, x2 first, and then okay, this player two gonna, based on the x1, x2 given, they're gonna minimize it. And from the role player's perspective, they're basically kind of choosing x1, x2 in such a way, right? Will make sure that they would maximize their sort of reward. Okay, so you can write it down, this max-min kind of a procedure as a linear programming as below. Okay, so here you need to introduce additional variable, which is that. So that's basically the lower bound of any of your choice from column two. Sorry, any of your choice from column player. So, and then what you want to do is to say, I want to maximize it. I want to maximize it, right? Because I want to make sure that this is a lower bound of either of the case. I want to maximize that. And whereas the column pairs basically is to say, okay, I want to choosing one of them who has the lowest value. But for now is that I only looking at this formulation is that I don't really sort of introduce column two's decision here at all, right? I just introduce this ended random variable that, so not that a random variable, but variable is a lower bound of each of the choice, because it's a minimization here, and we're gonna basically maximize that value. And of course, here is really to make sure that this is a probability, right? So if this is a sort of a simple LP problem can be solved by simplex solution or other solution. And then you can actually show that, the x1 is 3 out of 7, x2 is 4 out of 7, and z is 1 out of 7. So you can do the trick for column player as well. In other words, that is starting with the column players to say, I'm gonna maximize, and then for the opponent, I'm gonna minimize, and can do that. So you can do the same thing, right? And this is sort of a lower bound for this role player, and then we basically gonna maximize lower bound. I can do that. So you can find it's very interesting. These two solutions consistent with each other, right? This got the xy is 2.7, and x1 2.7, x2 is 2.7, and it's the w is minus 107. This is from this from this role player perspective, but from column player perspective, from role player perspective, the z, the lower bound, is basically 1 minus 7, and here the lower bound is my minus 1.7. So this is basically the game, the value of the game, and from a different perspective. So they are consistent. If you look at this a solution for LP1, LP2, okay, then number one, we observe that the payoff is they are sort of from adding together as a 0. So that means that this must be something consistent between these two LP solutions, right? And then you can look at that is from strategy X, which is from role player perspective, is that no matter what the column player gonna play, and you would get at least 1 out of 7 reward. Equally, you can looking at from Y perspective, no matter what no matter what role player gonna play, they would always get a pair of at least minus 1 out of 7. So, because it's a 0 sum, they're actually added together, right? So then you can immediately sort of guess that maybe these are best response to each other, isn't it? It's but it's different with the Nash equilibrium because we didn't really start with the Nash equilibrium. We somehow end up with Nash equilibrium, and because this sort of Nash equilibrium requires this sort of best response, but in fact here is best response to each other. They have to condition on the other strategy, but in this case we don't. Well, we will not really formulate that because we formulate as a linear programming solution, and they are formulated independently. So, and also it seems that one of them sort of review their information first and review their strategy, and that other players' response. And in fact, they feel that they didn't have that sort of a disadvantage like what we had in the Connors, bi-level game case. There's a sort of an underlying reason of that is because of this connection to this LP solution, the duality in the LP solution.